we're going to move on to Stephanie Gowell. Apologize there. And plume surface interaction impingement to facilitate lunar exploration infrastructure. You ready, Stephanie?
Yep, I'm ready.
Okay, great. Thank you.
Thank you.
Go ahead.
I'm Stephanie Gowell at Maston Space Systems. I'm a business development engineer. Next slide, please. I thought I'd start with going over kind of who Maston Space Systems is and what we're doing, and then go into the details of our work. So Maston Space Systems is a lunar lander vendor in the NASA CLIPS program, providing lunar surface delivery on our Maston Mission 1 in December 2022 for NASA and commercial payloads. Our lander is designed to safely deliver multiple types of payloads, such as science instruments, rovers, and technology demonstrations to the lunar South Pole on Maston Mission 1. This is the first landing for Maston's recurring lunar surface delivery service, which will facilitate lunar exploration infrastructure and enable a sustained human presence on the moon. One of the technology gaps that Maston is researching to help enable this future is plume surface impingement. Next slide, please. This slide's my favorite slide. This is an actual picture of some of the work we have done with our partners at the University of Central Florida, Drs. Phil Metzger and Dr. Adrian Dove. This is our reusable Zodiac launch vehicle out in Mojave as part of our plume surface interaction testing. So plumes generated from descent rockets impinge on the lunar landing site regolith, rendering sites hazardous for landing due to possible deep cratering and ejecta. Maston Space Systems and UCF are studying the regolith cratering effects in different plume environments to understand cratering physics and also landing pad durability. Testing consists of characterizing lunar surface ejecta particles by size, velocities, and trajectories during rocket-powered landings and ascents, and determining the rate of mass ejection from cratering. Preliminary drop tower and rocket engine tests show scalable results. Our data demonstrates the importance of developing methods to mitigate the effects of cratering and ejecta to enable a sustainable lunar presence.
Stephanie, you have 1 minute remaining.
Thank you. Testing in low gravity and vacuum conditions is in progress, and we're looking at different sizes of landers. They're being investigated with a path from CLIPS to HLS Artemis landers. Next chart, please. Feel free to reach out to me at the second address there, or our team at moon@maston.aero for more information, or if you're looking to test your payload out or demonstrate it on a future lunar mission. Thank you for the time.
Okay, great. Thank you for that talk.